So I hope you've been watching the Tyler DeWitt videos about how to write formulas for ionic compounds. He is pretty awesome. And, going forward, he has videos on just about everything. So if something that we're doing doesn't make sense, he is a really, really good resource for you to use. There was one video that I couldn't find of his. It may be out there. But I wanted to show you how to write ionic formulas if you've got something that's a transition metal, because on the last video that you watched of his, he just had like this whole middle section of the periodic table just kind of blanked out, and he wasn't talking about these at all. And it's very, very easy. It's just like the other formulas that he was writing, but you just can't predict the charges of these elements from the periodic table, and that's what makes this one different. You know how he had like each of these charges written in, so this group's always +1, this group's always +2. If you've got your periodic table there, write these charges in as you're getting used to working with these. So this would be +4 or -4. And so we call these the representative elements. These are the ones that are very predictable. But again, these transition metals here in the middle are not predictable, with a couple of exceptions. So we're talking about these groups here. But really it's easier if you're writing formulas with these, because what's going to happen with these particular elements is they're going to have to tell you what the charge is, since the charge is not predictable. So if you have a formula that you need to write for something that has a transition metal in it, the name of that compound is going to look something like this. So it might be copper 1. So it's got this Roman numeral here that the others don't have. And let's just do sulfide. So copper 1 sulfide. What this Roman numeral tells you is the charge on the copper ion. So what this means is I've got copper with a +1 charge, and I have sulfur. I'm going to go back to my table, just like we were doing in the previous video, and I look at where sulfur is on the periodic table, and I see that it has a -2 charge. So the way Tyler DeWitt showed you how to do this is you just start putting in ions until you get the charges to cancel each other out. The total charge needs to equal 0. So since sulfur has a higher charge than the copper, I'm going to write in another copper. And so that's going to give me 2 positives and 2 negatives. And so my formula is going to be Cu2S. Now, there's another little trick I want to show you that will usually work if you don't like writing out everything here. It's called crossing over, and you can find other videos and websites that talk about this. But it almost always works. Sometimes you do have to reduce your numbers, just like you would reduce a fraction. But if you look at these charges, look at the absolute value. Don't take the charges with them. But basically, when you see the charges of your 2 ions, you just switch the numbers. So since this has a 1, I know that I need 1 sulfur. Since the sulfur has a 2, I know that I need 2 coppers. And so, again, I'm crossing over the numbers, but don't take the charges with them. And so that's another way to get the Cu2S as your formula for copper 1 sulfide. Now, again, the reason we have to have this Roman numeral is because there are other possibilities for copper. Copper can also have a +2 charge. So the copper ion with a +2 is going to be copper 2, and let's put it together with chloride. So if I need to write a formula for this, again, this always tells me the charge on the first ion. It's always the first one. It never goes with the second one. So that tells me that I've got a copper ion with a +2 charge. I've got a chloride ion, which comes from chlorine, as hopefully you know. And so chlorine is in this column 17. always has a -1 charge in an ionic compound. And so I'm going to cross over these charges. So the copper has a 2. That means I should need 2 chlorines in the final compound. The chlorine has a 1, which tells me I need 1 copper. Of course, that's understood at the end. And so if you look at this, 1 + 2 gives me a total +2 charge. Here I've got 2 -1s, which gives me a -2 charge. And so those will cancel each other out. And my final answer here is CuCl2 for copper 2 chloride. Hope that's making sense to you. Let's look at 1 or 2 others, just a couple of examples. If you've got this, stop the video and move on. That's fine. How about iron 3 oxide? So I'm going to find the symbol for iron on the periodic table. It's one of the trickier ones. Fe is iron. Again, it's in this transition metal region of the table. So I don't know its charge except for the fact that I have this Roman numeral here. So that is the charge on iron. I've got a +3 charge. For oxide, I'm looking at oxygen on my periodic table. It has a -2 charge always because of the column that it's in when it's in an ionic compound. And so I see that these 2 charges do not balance each other out. Again, I'm going to do the crossing over method. If you want to do the method where you write them out, that's perfectly fine. So I see that iron has a 3, so I'm going to put a 3 with the oxygen. Oxygen has a -2 charge. I'm going to put the 2 with the iron. And again, just double check and make sure. 2 +3s give me a total +6 here. 3 times -2 gives me a -6 there. So those 2 cancel each other out. So my formula is Fe2O3. And again, notice I don't bring these charges down into the formula because this compound overall is neutral. The charges have canceled out. And I think Tyler DeWitt, if you watched that video, made a big point about that. So there is your formula for this one. One more. I told you that this method, the crossing over, sometimes will give you a little bit of trouble. The only time you're going to run into trouble again is if it's not reduced down to its lowest terms. So let's say I've got something like chromium, Roman numeral 4, and let's do oxide again. So my 2 ions here are the chromium ion with a +4 charge. Chromium is Cr. The oxide ion, just like we did in the previous example here, has a -2 charge. I get that from the chart. If I cross these over, I'll get a 2:4 ratio. So I just need to reduce that down just like you would reduce a fraction to get it into lowest terms. So my actual ratio here should be a 1:2 ratio. And so my final answer is CrO2. Again, if I look at these numbers, I've got a -4 charge on the negative side, a +4 in the 1 there. I've got a +4 charge on this side. So since my 2 charges here cancel out, I know that I've got the correct formula there at the end. And so that's all there is to using Roman numerals for transition metals. They look just a little different, but they work pretty much the same. Now there's one more thing I need to tell you about this. Maybe I should have started off with this. There are a couple of exceptions to the Roman numerals. For some transition metals, you won't see a Roman numeral. So these are the ones you need to know. You have cadmium, Aluminum is not really a transition metal, but sometimes it's included in this group because as we look at the periodic table, and you think about where the metalloids are, as you separate those out, let's see here, there's your stair-step line. Some of these metals over in this region of the table, like aluminum and lead and tin, are considered to be in with these transition metals. So I need to, or I include that one sometimes, even though you can predict its charge from the chart. Aluminum's in that group. So cadmium, aluminum, silver, and zinc. If we were in the classroom, you'd hear me saying these over and over and over. These are your exceptions. They have charges that are predictable. They don't change. Cadmium is always +2. Aluminum is always +3. Again, it can be predicted from the chart, but it's usually included in this group. Silver will have a +1 charge, and zinc will have a +2. So there's no easy way to keep up with those except just to memorize those elements, 3 of which, of course, are true transition metals, and then the others are, or the aluminum there, of course, can be predicted. So that's what you need to know about writing formulas for ionic compounds when you're using those transition metals. Hope this was helpful.